Unit 1.2C's first example, number 1, should hopefully feel a little bit familiar, and so I'm hoping you were able to do this without my assistance. But if you're not, we're going to go over the problem and hopefully clear up any questions that you have. So for the first example, it says ultraviolet light with a wavelength of 92 nanometers can remove the 3p electrons of aluminum. How much energy is needed to remove one 3p electron from aluminum? How much energy for 1 mole of 3p electrons? So with any of these problems, we're talking about nanometers or wavelengths or things like that. There are really kind of two equations that we can work with depending on what we're up to. There is the energy equation, E equals h nu, and there is the speed of light equation, C equals wavelength times frequency. Depending on the type of problem that you are watching or doing, you're going to use one or both of these, and it kind of depends on the context of the problem. So the trick with a lot of these is that you just need to read carefully. So when we look at the information we're given, we are given a wavelength. It tells us the wavelength of 92 nanometers. You should automatically think in your head in this situation, if you give me a unit in nanometers and I have to do any math, that is useless to me, person writing the problem, and I need to turn this thing into meters. But let's read on to make sure that we confirm our suspicions. Extra information here, all this is delightful, but the thing that's asking me is how much energy. So if we're asking for energy, we are going to need to use the equation E equals h nu, okay? So we've got E equals h nu. Its frequency is not given in the problem, so that means I'm going to have to use both of these. And that does mean that my 92 nanometers needs to be turned into meters. So I'm going to do that first and foremost. 92 nanometers. There are 1 times 10 to the 9th nanometers in a meter, 1 meter on the top, 1 times 10 to the 9th nanometers on the bottom. So that cancels out. Then let's check our math. That's kind of icky. So we are going to end up with 9.2 times 10 to the negative 8th meters. So we've got a wavelength here now that's useful, and we've got these two equations. Well, the only equation that has wavelength in it is the one with the speed of light. So we need to figure that out. Again, this again should feel very similar to the 1.2b example that we went through. So C equals wavelength times frequency. I want to find my frequency, so I'm going to divide by the wavelength. And so my frequency is equal to 3 times 10 to the 8th meters seconds to the negative 1 divided by my wavelength, which is 9.2 times 10 to the negative 8th meters. Okay, hopefully this is just very familiar from the previous problem. So I've got my two numbers here. I'm going to put them in the calculator, and hopefully you are feeling a little bit more confident with your calculator that I don't need to show you. But my problem answer comes out to be 3.26 times 10 to the 15th seconds to the negative 1. The meters cancel out, and when I divide them, I get 3.26 times 10 to the 15th for my frequency. Then I can put my frequency into my energy equation. So my change in energy is equal to h, Planck's constant, times nu. So that Planck's constant is 6.626 times 10 to the negative 34th joule seconds times my frequency, which is 3.26 times 10 to the 15th seconds to the negative 1. Now, what I've seen in the past with some students is that they just put in the symbol for frequency, and that's not going to fly. You actually have to put the numbers into the equation and then show that work. Seconds and seconds to the negative 1 cancel each other out, and we are left with an energy value of joules. And if I multiply those things together, I get a value of 2.16 times 10 to the negative 18th joules. All right, so that is the energy for one photon or one electron that's removed. Okay, So in this case, we're talking about electrons, not photons. So this 10 to the negative 18th is equal to 1 electron being removed. The question then for the second part is how much energy does it take for 1 mole of 3p electrons? So it is 2.16 times 10 to the negative 18th joules for 1 electron. Rack your brain. Think about how many moles would be in an electron mole. So how many electrons would be in a mole of electrons? Oh, there's that number. Something times something. It's called the Avogadro's number, and it is 6.02 times 10 to the 23rd. So there are going to be 6.02 times 10 to the 23rd electrons for 1 mole of electrons. And when I multiply these two things together, I end up getting 1.3 times 10 to the 6th joules. Now I put that in scientific notation because I find huge numbers to be super obnoxious. So I would encourage you to do that as well. Sometimes what will happen is they will put something in kilojoules instead. And so I'll show you that. 1.3 times 10 to the 6 joules, if I wanted to convert that to kilojoules, there are 1,000 joules in 1 kilojoule. So, excuse me. So if I wanted to figure out how many kilojoules there were, I'll put this in here because I'm doing this on the fly. You get 1,300. Okay, so what this means is that it would take 1,300 kilojoules, or 1.3 times 10 to the 6th joules, to make the mole of electrons leave that particular atom. So it's up to you how you want to report them. I would just really appreciate it if you didn't leave me this number, because that's kind of obnoxious. Okay, so we don't want that. Either record it in scientific notation or in kilojoules. If it's not specific, you can put it in either, and either would be acceptable. But I prefer it in either joules or kilojoules. Okay? If you have any questions, let me know.